Introduction. One of the primary goals of the artificial intelligence field remains open. This is the development of autonomous systems capable of performing self-directed tasks in a similar way that humans do. Challenges and issues involved in the development of autonomous systems deployable in dynamic and open environments have led to fields as multi-agent systems. It is a discipline that forms a profound interdisciplinary study of fundamentals such as autonomy, agency, negotiation, communication, interaction, and cooperation. The major objective of this field is to develop autonomous systems capable of coexisting and cooperating with people and other systems in the real world. The principal motivation of this effort to develop autonomous systems is related to how people live in a digital and interconnected world, where new challenges and opportunities are arising, for example, Internet of Things, IoT, smart cities, and big data, as consequence of technology is strongly embedded in our daily life. Thus, we are near to see in our local environment, autonomous systems like smart environments, rural and urban scenarios, humanoid robots, unmanned vehicles, aerial and ground, among other autonomous systems capable of supporting people in their daily life. An important feature of these systems is the autonomy because they must be capable of embodying self-governance and decision-making. In this sense, to ensure that the autonomous systems are useful, they should be endowed with the ability to exhibit a smart negotiation to achieve its goals through the cooperation. It is supposed that these properties enable distributed systems to improve their performance. Negotiation enables multi-agent systems to achieve their goals. Although there are several research achievements that concern strategies and protocols in the field of negotiation nowadays, its implementation and applications in real-world scenarios is still far to reach. In a general sense, the multi-agent system, MAS, is a paradigm in the computer sciences and related areas where a system of interest is conceived as a set of autonomous entities called agents, as well as its interaction mechanisms. The agent is an autonomous entity with the ability to sense the environment through a set of physical or logical sensors and to interact or modify such an environment by a set of physical or logical actuators, as well. A kind of intelligence or inference mechanism is also conferred to an agent. Thus, actions to the environment are based on the sensors and the inference machinery. The MAS approach has proved to be a suitable solution for problems of distributed nature, where the information, the control, the processing, or all of them are not centralized but rather distributed. Thus, a set of problems has been well studied and useful solutions have been obtained. The interaction among agents is generally considered as message passing based on a well-structured interaction protocols. The content of the message is information that may lay in a context called ontology. Figure 1 depicts a general layout of a MAS accordingly Foundation for Intelligent Physical Agents, FIPA. General layout of a multi-agent system. The Foundation for Intelligent Physical Agents, FIPA, is an IEEE organization promoting the technology and standardization of multi-agent systems. FIPA defines a set of specifications in the basic layer for the agent communication, management, and message transportation, as well as specification for the abstract architecture and applications layers. The interaction protocols, communicative acts, and the content of the messages interchanged between the agents are covered by the specifications defined by FIPA. For example, the auction and call for proposal mechanisms among a set of agents are defined as interaction protocols in the FIPA specifications. The automotive industry is moving toward the automated mobility. To achieve the goal of making mobility safer and having an optimized system for moving people in the world, a visionary technology is needed. The approach followed in this lecture is based on MAS applied to the automotive scenarios. The Internet of Things, IoT, is part of the design, as it is a trending technology for the connected cars and smart cities. The applications of MAS to automotive applications, like traffic management and load balancing problem, include multiple possibilities, since the agents could represent different actors in the implementation of the solution. For example, the authors identify 5 types of agents: pedestrians, vehicles, traffic lights, streets, and parking lots. In this lecture, we consider the use of coordinators, route agents and traffic light cycles, phases, as an extension to the entities involved in the traffic manipulation. The use of pedestrians as agents suffers from the problem to manage the communication with other agents. For example, Other agents like vehicles and traffic lights can be incorporated with electric source and wireless link that helps power sensor systems or technology to help them accomplish that purpose of communication. Though, pedestrians normally do not have the facilities to perform those functions, however, the benefits to consider pedestrians as agents can be substantial due to obvious reasons. An approach to incorporate pedestrians into the system is to use a mobile device, such as the smartphones. By using these devices to identify pedestrians, its sensors may allow to monitor the position of the pedestrians, among other cases. Other examples of vehicles as agents are reported in and. These works consider the communication between vehicles to coordinate the routes every vehicle should take to reach its destiny. Within this approach, every vehicle has information that helps them to accomplish their goal, which deals with moving from point A to point B in the shortest time possible. The agents or cars can share or keep this information according to its heuristics, which are the rules they use to make any decision that push them closer to complete their goal. Making local individual decisions based on information gathered by themselves or cooperating with other agents help they accomplish a global goal of coordination between vehicles in such a way that every agent can reach their destiny in less time than picking the common fast routes, and sometimes creating bottlenecks on those streets or avenues. Another popular approach is to focus on traffic lights, since they are typically the most common points where traffic loads are introduced into the system. There are several papers focusing on intersections like. These works focus on coordination of phases between different intersections. The hypothesis is that creating local solutions in each intersection will produce a better performance overall in the system as a whole. And the authors propose using a set of Q-learning iterations to approach the optimal solution of load balancing. They also mention several methods to control the traffic lights and intersections using different techniques of the artificial intelligence, such as fuzzy rules, predefined rule-based systems, and centralized methods. An important feature of this approach is that when controlling traffic lights and intersections, the phases that control traffic in different roads are a key element for the success of the goal of the system. Indeed, the coordination between changes of lights and what streets have preference before others are crucial to get a good traffic flow in the right direction. This feature is considered in this lecture. Other important example that implements multiple agents as a solution to automotive scenarios is. In this work, the focus is to make buses arrive on time to their stops. The system uses 4 agents: the bus vehicle, the bus route, the intersections, and the stages. The bus vehicle drives through the route informing the route agent their times. The route agent checks the time between the buses in the same route, and if the buses are late or early, it communicates with the main agent, the intersection. The intersections analyze what to do. If the bus is too early, then the stages where the bus is not currently transiting have priority to be set in the traffic light. On the contrary, if the bus is too late, the stages where the bus is going should have more probability of appearing in the traffic light. One important aspect to notice is the priority. Having a greater priority does not mean that automatically that stage will be next. It only gives to the agent more tools to coordinate with other stages to be the one at the top, which is a goal. The stages need to coordinate, and from that process, the next stage in the traffic light is selected. The coordination is selected by multiple factors: the number of buses in the lane, the green time required by the stage, the velocity of the vehicles in the lane, etc. based on the specifications defined by FIPA. Several implementations provide frameworks for the development of MOS. For example, the Java Agent Development (JADE) framework is a platform for the development of agent-based applications. JADE is fully compliant with the FIPA specifications and provides a basic class for agent instantiation, communication protocols, ontology implementation, and graphical management tools. Figure 2 provides a reference model for the management of agents within the platform.